So back onto our Z80 project. In the previous video in this series we'd got as far as being able to send data from the PS2 keyboard through the PS2 interface. It would generate an interrupt and then the Z80 would pick up that data and it would send it through to the video output and we'd see it on the screen. But it wasn't interpreting the data into ASCII form, it was just printing it as the raw values that were coming through. And each time you press a key on a PS2 keyboard you will generally get more than one data packet being sent. So the keyboard will send a data packet when you first press the key down that relates to the particular key you're pressing. It will then send a specially coded data packet when you first release the key, and then it will send a repeat of the code for the particular key. So you'll generally get at least 3 data packets each time you press and release one of the keys. If you hold a key down you will initially get the character code or the scan code for the key that you've pressed, and after a short delay it will start repeating that scan code, and then when you release the key you'll get the specially coded byte followed by the code for the key again. If you hold the shift key down it will send a code that relates to the particular shift key, whether it's the left or right shift key. If you hold the shift key down and press another key it will send the code for the key, but it will be the same code it would send as if you didn't have the shift key pressed. So in other words, if you press the A key without any other keys pressed it will send a particular code. But if you press and hold the shift key and then press the A key again, it will still send the same code for the A key, but it will have sent before that the down code for the shift key. And the left and right shift keys send different codes, but it's up to your system to keep track of whether you're in shift state or control state or alt state. The codes sent by each key are always the same. So what we have to do in our handler is to modify it so it can keep track of the particular part of the sequence it's in, whether we're in shift state, whether the key's just been pressed or whether the key's just been released, and it has to interpret the characters accordingly. Now, as I've said in a previous video, someone did suggest it would have been easier to use an adapter of some sort to convert between the PS2 code and our system. And I pointed out that that would kind of negate the point of this project, which is to design a system from scratch using logic devices in a similar way it would be designed back in the 1970s and 80s. But also in this video I want to show how that's not even a very good solution. It would make life more difficult for us in the long run, and shortcuts when you're designing something like this are almost never a good idea. It's better to do the work yourself and you may end up with a better design. One thing's for certain, if you don't design it yourself and you just get an off-the-shelf solution, your design won't be any better than what is already available. So what I want to show in this video is the progress I've made and also why off-the-shelf solutions aren't always the best. So what I've done since the last video is write the handler for our keyboards. That's the keyboard interrupt handler, and we'll have a look at the code later on, but we'll start by looking at the flowchart. So this is normally how I start writing these blocks of code. I'll turn it into a flowchart, it just makes it easier to write the software. So it's a fairly simple process to convert the PS2 code. So the first thing that happens when the interrupt is thrown is the Z80 reads the data that's been received by the PS2 port. Notice this does not need to handle the bit bashing, it just deals with the complete data byte that's been received using our hardware solution here. It then reads some flags that have been saved into the RAM when we initialize the Z80, and these allow us to keep track of if a key's been pressed, if we're in shift state, if the key is currently down or if it's been released, and so that enables us to then process the data byte that's been received. So is this, for example, is it the release code? You probably can't read this, but it's fairly straightforward. And if it is the release code, it sets a flag and then does nothing more but save the flags and will exit the handler. If it's not the release code, it checks to see if it's the shift code, and if it is, it checks if the release flag is set. So in other words, are we releasing the shift key? And if it is, it clears the shift key and the release flag. If the release flag is not set, it means we've just pressed the shift key, in which case we've gone into shift mode, so it sets the shift flag, saves the flags. If we get through this, it means that we've received a key and we're either in shift mode or we're not. And the first thing it checks after that is to see if we're releasing the key. So it might be we've pressed the D key and then we've released it, and this part of the code is checking to see if it's the key down or the key release, or if the key is repeating. And we'll have a look at this on the screen in a few minutes. And then it goes on to process the character that's been received. If the shift key has been pressed first, we're going to shift mode, in which case it modifies the pointer into the lookup table that it uses to convert between the PS2 scan code and ASCII code, and then it will go through and do whatever it needs to with the character. When we come to writing the full handler for the Z80, the boot ROM, we'll deal with what happens to the character that's been pressed in the main part of the program. But for now, I'm actually just using a very small loop within the interrupt handler to send that to the screen. As I say, later on we'll have a circular buffer that stores the characters that are being sent from the keyboard. And in this case it also saves the character to a buffer, exits, and that's it. And it will keep going through this each time a packet is received from the PS2 keyboard, and it in theory should handle the keys, the shifted state of the keys. And the interrupt handler is a bit more complex than this, and I'll explain what I've added to it in addition to this sort of basic flowchart, and also why I was saying that ready-made solutions aren't always the best. But before we do that, I'll move the camera so you can see the screen, and we'll see what we can produce at the moment. I'll press one of the keys, I'll press the H key, and notice we are getting a lowercase h. If I hold the key down, it will repeat. Try different keys, we are getting the correct characters. Try the number keys, and that's working correctly. And I'll press the shift key. Notice it's not showing anything on the screen, as it shouldn't. I'll press one of the other keys and we're getting the uppercase character. And so that is doing exactly what it's supposed to. So I'll move the camera back and we'll have a look at some other changes I've made. So now that we can display characters on the screen and we can correctly interpret them, the next step is to create the cursor. And there's many ways you can create a cursor on a design like this. You can have hardware counters and coincidence testing, so when you get to the part of the screen where the cursor should be displayed, you have a couple of counters for X and Y for the cursor, and when they match the current position that's being scanned by the video output circuit, the cursor is created. In our case, you may recall from an earlier video that I decided to use a spare bit on the SRAM data to store the cursor information. So when that bit is set, we use that particular character as the cursor generation. So small piece of additional circuitry to allow us to do that. However, one of the things we need for that to work correctly is to be able to read from the video RAM. It's okay if we're just typing characters in and we'll just set the bit as each new character comes along. But if we want to move the cursor around using the cursor keys, we need to be able to read the character from the screen RAM, because if we move the cursor into a particular location and we want to move the cursor to that location, if there's a character there, let's say there's an uppercase G in that location, then we need to read that character first, set the cursor bit, and then write the character back to that location in SRAM. If we can't read it, we don't know what character's there, and we'd end up overwriting whatever data's already on the screen. Now in reality we kind of need to be able to read the video RAM anyways. Anyone writing any serious software is almost certainly going to want to be able to do that, and so we'd probably include that feature irrespective of whether we needed it for the cursor generation at all. So I'd already built that in, and you may recall from the circuits I'd shown previously, let's grab a copy of it, that what we had was a buffer that allows us to send data into the SRAM, so this is a bidirectional buffer, or to read data from the SRAM, and there's some control logic down here. Now that control logic has two lines. It has a write line that's active low, and it has a read line that's active high. So we need to be able to send the appropriate level signals to those two lines in response to the Z80 executing a read or a write instruction, and we don't want to have special handling for accessing the video SRAM. We want to be able to just do a read or write to memory. So all we need to do is a very simple addition, and we can do something this simple because the system and the circuits have been specifically designed with this in mind. Until now we've been triggering the write function of the SRAM when we've sent data by connecting the video RAM chip enable line directly to the write line of the video system. But we can't do that, of course, if we want to read and write. We need to be able to distinguish between those two, and so all we have to do here is pick up the memory write line, which is part of the memory decoder, or the memory read line, and derive our two control lines from those, and then we use these to control those two lines going into the video RAM. So if we want to do a write, then it will trigger this line. If we want to do a read, it will trigger this line, and these are of course controlled by the Z80 when it does memory read or writes to the video RAM. So we now have what we need. We can read and write. It's just a very simple addition, just 3 logic gates. We already have these spare on the Z80 board, so once again we don't need to add any additional components. They're not on, although the components are on this board, they're not connected, so I've added this board on top. So I'll move the camera back across to the monitor and let you see what this now produces, and then we'll have a look at the interrupt handler itself and look at the code that's doing all this. So what we can do now is move the cursor around. Now I've specifically not been drawing the cursor when keys are being entered to allow me to properly test the system. But when we move the cursor around, of course, we need to display it. So if I press the down arrow, notice the cursor appears, and if I keep pressing it, the cursor moves down. If I press the left or the right or the up, we can move the cursor around, and we can move it, of course, to anywhere on the screen that we want to. And of course, enter text. So this is now getting much nearer to a working system, and what we end up doing with this is going to be dependent on the main boot ROM and the monitor program that we create, or even the user applications. But of course it does mean that we can now start testing the system much more in depth and start writing functions to test it much more carefully. But as you can see, it's working very well. I've zoomed the camera in, so hopefully you can see this a bit more clearly. But for the cursor system to work, it of course needs to be able to read the data from the SRAM and then set the cursor bit and write the value back to the video RAM. And you can see that working here. So if I move the cursor to the left, as it passes into each character position, you can see that the character is not being deleted or modified, it's just being inverted. And to do that, of course, it has to be able to read the character, set the cursor bit, and then write the value back into SRAM. And that's actually working. You can see that working well here. And so the cursor system is doing exactly what it's supposed to. that's working very well. So I'll move the camera back. You may remember when I was discussing the design and the circuits of the video system that I'd added this buffer chip, and when I showed the breadboard version of the video output, which is this, there was this buffer chip, and I said at the time that for the test purposes on the breadboard this could actually be removed, but it was here because we would need it later in the design. So I'll now explain what this is for, and I'll try and demonstrate why it needs to be there. So as I said, it's this buffer here, and the reason we need this is because the way this system works is we have the SRAM here that holds the video data, the character data of which particular characters we want in which particular position, and that data is sent through to the character ROM, and the character ROM then selects the particular part of the character bitmap depending which row of the character is being displayed. But because of the way the system works, the data from the SRAM needs to be buffered, so it needs to be read into the buffer, so it's presented to the ROM in a fairly static way. We don't want it to keep changing, because if we decide to read or write data to the SRAM, and also as this cycles normally, this data will change, and we can't really have that part way through loading the shift register. But once we've loaded the latch, then what we can do is anything we want on this side of the SRAM data bus, and the data will continue to be correctly shifted out of the shift register or loaded into the shift register after it has after the ROM has a chance to select the appropriate data. If we don't have this here, then we'll get some fairly odd behavior, and I'll demonstrate now what the system would do without this. And it's one of these things that if you're not aware of this, you might think there's something very wrong with the design of your video system, or the timing, or something else, or the software. But it's quite interesting, so I'll show what the system would do if we try removing that. So I've got the system powered up, and if I start pressing keys, it will appear to be working fine. So we'll try shift, that works. So everything's working fine, and as I said, the reason that the latch needs to be there is to allow us to manipulate the data that's in the SRAM without disrupting the display. So if I start pressing the cursor keys and we move the cursor across the screen, it seems to be working fine. We can go up and down, left and right. It all seems fine. However, if I carry on moving across the screen, you'll notice we'll get to a certain point and we get two cursors. And if we move around, you'll see the cursors move up and down the screen. If we keep going across, that will disappear, and when we get across to the end, the cursor should of course now appear on the next line down, but instead it disappears and we get a very narrow, it looks a bit like a vertical single line cursor on the left of the screen, and if I move across again, the cursor appears. So it's almost like it's going into a kind of dead area. And it looks for all the world like we've got an issue with the counters in the video system. But this is just caused by the data in the SRAM not being presented properly to the character ROM, and it's changing part way through being loaded into the shift register. And that's because the data is not being latched. That's why we need that latch in place. Without that, we can't really properly manipulate the data in the SRAM without running into these peculiar modes of operation. So as you can see, the latch needs to be there. If we don't include it, we'd get all sorts of odd behavior. So the last thing we'll do in this video is to have a look at the code for the interrupt handler. It's fairly straightforward, but one of the things that I've included is the cursor control code. The reason I've included that in the interrupt handler is because it's a very efficient place to put that. And in fact, this is what I was talking about earlier in this video when I said that not using a ready-made solution would work in our favor. And this greatly simplifies the operation of the system by not having these characters come in as ASCII code. So what we've got, I'll move the camera down a bit further so you can see this a bit more clearly. So as I said, this will start now to form the basis for the development of our boot ROM. So it's starting to take on a bit more of a formal appearance. One of the things I like to do when I'm writing code is to create what really amounts to almost like a pseudo language for the particular application. So in this case, I've actually created equates that might be a bit counterintuitive at this point. So I've got an equate here that's called bit 0, for example, that just means 0. So we could use the 0 in the code or bit 0. Now sometimes I might want to swap the bits around, so this is quite a convenient way of doing this. But more importantly, this allows me to distinguish between when I'm talking about something like maybe bit 0 or a port, which would be port 0. So rather than just saying 0, the code becomes much clearer, because in the code it would say bit 0 or port 0, which is a lot clearer than just saying 0. I hope that makes sense, but it's personal preference, but I prefer to do this, so you'll see this sort of thing appearing quite a lot in the code as we go through it. We've then got some system equates. In this case, we've seen these before. These are just the memory locations for the various things. Some system variables, so we want to store the flags and pointers, this sort of thing. And these are in the common RAM area. Or some of these are actually bits, and these are bits of maybe a flag byte. So for example, this character available flag is one of the bits within the keyboard flag, but identifying it this way makes it very clear in the code, as you'll see. The code then starts. We jump over some dummy text here. This is just, as I said, because this is going to form the basis for the structure of our boot ROM. We then initialize the interrupt mode we're going to use, load the iRegister, initialize the stack pointer, and then we load the value into the interrupt handler table that we're going to use for our particular interrupt handler. We clear the video RAM, and then once we've done that, we enter a very small indefinite loop. So the Z80 will just spin around this loop indefinitely. And what it's doing is just waiting for an interrupt from the keyboard. We've then got the lookup table for the conversion between PS2 and ASCII. There is another shortcut here that, again, it's an advantage we can have by not using something such as a ready-made converter, and it's something I'll come back to in a later video, but in the meantime you might want to have a ponder about what that could be. But it will make interpretation of printable and non-printable characters much more efficient within our code, and it's something you couldn't do with the ASCII equivalent. Okay, so we end up with our interrupt handler. So this is where we end up when the interrupt is thrown in response to us pressing a key. So this is really taking care of the flowchart we looked at earlier. So we push a few registers to save and be able to restore them, because we're going to be modifying these, and of course we don't want the system crashing. We're not using these anywhere else, but we will be at some point, so we might as well write the handler now to take care of the housekeeping that will be ultimately required. We've then got a load of the keyboard flags, so we want to load the flags that have been saved. These are saved into a location of the DRAM, of course, our main system RAM, but it's in the common RAM area, so we'll be able to run this interrupt handler irrespective of which bank is selected within the system. We then read the byte from the PS2 interface, and you recall this also resets the interface, so it will then be available to accept the next character, and it can be doing that while we are continuing to process the data. It's a very efficient way of handling the key presses. We then start effectively going through and carrying out the checks we looked at in the flowchart. So we check to see if this is the key release character. We then check to see, in this case, if it's a cursor key. So the thing I mentioned earlier that I'd added to the handler is cursor control. So we check to see if it's one of the cursor keys, and if it is, this short section of code here, so from here just down to here, it's about 30 lines of code, handle the cursor. So again, very efficient, and we couldn't do this efficiently if we'd received these characters as ASCII code. And there's an even more efficient way I mentioned that we can do this if we want to, because we have full control over the design. But what we're doing here is converting and dealing with the characters before we turn them into ASCII. So in this case we don't even need to bother turning these into ASCII if we don't want to. We can simply handle them as a really a command character and then finish. We don't need to then go on to convert it into ASCII. So a very efficient way of dealing with the processes of something like shift or cursor movement. But ultimately we end up checking the shift keys, and then once we've checked the shift keys we end up processing the actual data byte itself, and that's just this section of code here followed by this section. So again, very small section of code, and this is the advantage you get when you have a solution like this where we've created hardware that does most of the work for us. We can have what amounts to a 2.5 page interrupt handler that does the conversion of the character from the PS2 keyboard into ASCII. It deals with the cursor movement and it deals with shifting of the keys and selecting the appropriate conversion based on whether we're in shift mode or standard mode. So it's very efficient, and this is one of the benefits and advantages in writing code for a system where you design the hardware specifically for this application. So I hope all that makes sense. What I'm trying to get at here is that by proper design of our hardware, it really makes the writing of the code much more streamlined and straightforward, and that in turn means that most of the power of our Z80 is going to be available for our user applications rather than the housekeeping in the background that we'd have to do if we were bit bashing and whatever else, dealing with interpreting ASCII characters, that sort of thing, when we don't need to. So really starting to make some progress now. We've got most of the hardware we need for the basic system. What I'll be doing next is turning these circuits that we have in front of us here into a single board, and once the new board is available I will of course be able to start using the ZAX emulator that we looked at quite a while ago now to carry out the development, and that will save me having to program EPROMs each time we want to test a program. We can just do that directly from the emulator, test all the hardware, test the design, and use that to develop our boot ROM. So that will make life a lot easier, but really the next step is to get all this turned into a single board that we can use as our testbed.